wind energy students. Welcome back. We're now on to part 2 of our lecture about wind speeds and the measurement theory and so on. Now, this entire part of the lecture here is going to be about the wind speed distribution. And by what I'm talking about with the distribution, think like a histogram, okay? We want to know how often do winds of this strength happen, how often do the winds of this strength happen, and so on. Knowing this kind of information is going to help us understand the frequency at which winds of different speeds occur. I mean, in the context of wind energy, a common kind of problem to be asking about this would be like, let's say your wind turbine has to shut down for safety reasons whenever the wind exceeds, let's say, 20 meters per second. Okay, how often does that happen at this location? You could figure that out if you do the distribution of wind speeds at your location. Now, this unfortunately becomes kind of tangled because students get two ideas kind of mixed up, histograms and distributions. And I want to kind of see if I can help get this straight a little bit. I mean, I know what you think you're looking for here. You're looking for something like this diagram right here, where we're like, oh, I see, it's a bell curve distribution, where like there's a range over which, you know, we can see that there's a certain fraction of the time it happens, and it's more common along in this range, and it's less common in this range, and yeah, I'm not entirely disagreeing with that. Or, you know, here's another example. This is an exponential distribution I just overlaid here, where like, oh, I see over this range of very small values that happened a lot, and over this range of bigger values it happened less frequently. This idea that there would be like a plot showing the distribution over which something can happen. Well, any property that we measure will have some distribution to the outcomes of measurements. There'll be observations that are less common, and there'll be observations that are more common. While as an old stats major, I know that it isn't necessarily the case that all such distributions are mound-shaped or bell-shaped or whatever. In practice, in any kind of physics, engineering, science-type discipline, some kind of distribution that has a mound like that, like the 1, 2, 3, 4 distributions that I have on that graph up there, that's certainly by far the most common way for these kinds of distributions to look. And we're going to introduce you here to some kind of informal terminology that helps us describe distributions. As I've mentioned, when I was an undergraduate, I actually majored in statistics and atmospheric sciences, and in those statistics courses, kind of informally, what they call that mound to a distribution is called a puppy. And the word puppy, in this sense, comes from an expression about like a puppy under a rug. Can you picture like what it would look like when a puppy is under the rug? You sort of see that lump in the rug, but the puppy has, you know, he's gotten underneath the rug or whatever to play, and you can see that lump under the rug. That's this idea of there being a mound in the distribution. Like I got that clip art puppy there under the green curve here. And he is the puppy under the rug. The puppy is kind of an informal way that stats people talk about like the mound, the hump of the distribution, okay? Now, I have 4 different distributions on that particular graph right there. And like, for example, you can see that there's that green distribution there, and that would be a distribution of outcomes where we're measuring something, and you can see some outcomes are more common and some are less common, and that puppy, that mound here, has a certain height and it has a certain width, and you know, just speaking of it in kind of an informal way, we can see then that like there's a different puppy or mound or bell or whatever to like the blue distribution there, where that puppy is taller and narrower and shifted somewhat to the right. Those observations have a narrower range. They have more of their observations near the center of the observation. They have less tail to the distribution, and so on. Okay, these are just sort of informal ideas that we're going to try then to find ways to quantify. But we can kind of talk about how there's a difference between the green distribution there and the blue distribution, even though they're both bell curves. They're both standard normal distributions. Another distribution I showed there is that brown one, where you can see there's a very wide range of outcomes. Here the puppy is very broad but not very tall. And these are all just different ways of working with the so-called standard normal distribution. They just all have slightly different properties in terms of how wide the tails are and how long the tails are and how tall the mound or the puppy of the distribution is and so on. Alright, but they're all just ways to quantify and describe the distribution of outcomes that we'd expect with our measurements. And as it happens, the ones that I've been showing you so far have either been so-called standard normal bell curves, or there was that one that was an exponential curve, neither one of which very well describes the distribution of winds. The distribution of winds at any given location tends to follow what is called the WEIBULL distribution. That is a very tricky word, WEIBULL. It does not look like Weibull at all, because it is named after a guy who is ethnically Swedish, and his name is pronounced Weibull. But I certainly have heard this referred to as the WEIBULL distribution or the WEIBULL distribution, but the right word is Weibull. It is the WEIBULL distribution, and you can see an example of the WEIBULL distribution of winds in that graph right there. It's named after, I don't even want to guess how his first name is pronounced, Weibull. Vladimir Weibull. Anyway, he was, strangely, he was from France, but he was ethnically Swedish, and he has this strange name, and he actually discovered the math behind this Weibull distribution that is a really good fit to how winds are distributed at any given location in terms of their speed. He actually found that distribution in a completely different context. It didn't have anything to do with the winds or whatever, but we could see how we could apply this idea of the Weibull distribution and figure out what we can do with this. I mean, our x-axis here, you can use the Weibull distribution for lots of things. Certain Vegas games, for example, casino games, the outcomes are distributed by a Weibull distribution and so on. But from the point of view of like the wind energy, we could say that the x-axis here is going to be about wind speeds, maybe with units of meters per second or something like that. And then the y-axis is certainly telling us something about like how often this happens. But I'm going to go ahead and leave that a little murky. I'm going to be a little bit vague about what I think that y-axis is yet, because I think that's going to turn out to be a not easy point. So for now I'm going to call it occurrence or something like that. But what is that y-axis is going to be an important point. Some kind of measure, though, of how likely it is the wind speed right now is that speed. Okay, so if I kind of make the Weibull distribution here a little bigger here, I have this Weibull distribution, and there are a lot of things I'm really happy about with this Weibull distribution right to start with. For example, it has a lot of features I really like. I like the fact that there is no possibility of the winds being less than 0. That makes sense. There's no such thing as like a negative wind speed, right? So my wind turbine, my anemometer, whatever, is never going to encounter a wind speed that's less than 0, and that's exactly what the Weibull distribution says will happen. Okay, good. And I like the fact that even if you just go a little ways above 0, a wind speed of maybe 1 meter per second or something like that, it's a whole lot. Because weak winds are certainly very common. I mean, the reality is that's probably one of the most common winds that we're going to observe is, a wind that's pretty weak. That's going to be something important to know when you're designing where your wind farm is going to be and so on. Because when the winds are weak, you're not getting much of any power. Remember, the power that you extract from the wind, remember, is the flux of kinetic energy is proportional to the wind speed cubed. So if you have one of these low wind speeds, you have virtually no power that you're extracting. So we're going to need to know that. Okay, so we have these so far the Weibull distribution is making me happy. In fact, the Weibull distribution is going to make me happy. It's just that we're going to have to know what we're doing with it. I like the fact that there is some wind speed that is the mode of the distribution. Mode is a statistics term that means like the most common one. Okay, that's the peak of the distribution. See how the distribution is sort of a puppy? And the puppy is the peak of the puppy there. At the peak of the bell, or whatever you want to say, is at in this case, right around 5, maybe 6 meters per second, something like that. That was the most common observed wind speed. Okay, again, a good thing that makes me happy about the Weibull distribution, and I like the fact that the puppy's, the tail goes down way far off to the right on the diagram here. I mean, there is a finite real probability that the winds are 35 meters per second right now. It's just really, really small. But they do occur. I mean, if you're going to be building a wind turbine at this location, you need to know that there is a finite chance at any given time the winds will be at this very high velocity. Your equipment either needs to be able to withstand that, or you need to have procedures to shut it down when it's that windy for safety reasons and so on. I like the fact that it's got this mound-shaped distribution, kind of, a puppy underneath it, and I like the fact that I can do things to change the distribution. There are actually two parameters that you can adjust when you are creating the curves of the Weibull distribution that control its shape. One of which is the so-called shape parameter, which is given by the letter K in the equations that we're going to be seeing in just a little bit. And that is a number that makes the puppy, the hump of the distribution here, wider or narrower. You can adjust your Weibull distribution based on the observations that you get from a pilot study or something like that gives you a sense of like what's the standard deviation of the winds at that location. And we won't actually compute the value of K ourselves. We'll be given it in a problem or whatever, but you could certainly do it. And in this case, this particular Weibull distribution that I have on this diagram has a value of K of 1.5, but in fact, like on this diagram I found online, you can see that we can mess with the value of K over a range of values and get surprisingly different shapes to the Weibull distribution. Where, like the purple one looks very similar to the curve we had before, where it starts at 0 and then increases. There's a large number of low observations, then you reach the mode of the distribution, and then it tailed off to higher observations. In contrast to like that green curve, which is another Weibull distribution with a slightly different value of K. This is something that you can calculate based on like a pilot study where you get a sense of what the standard deviation of the observations is. We can do other things with the Weibull distribution. We can also shift the location of that peak of the mode of the distribution, the top of the puppy. You can shift that left and right by adjusting the so-called scale parameter, sometimes called a location parameter, and it is given by the symbol A in an equation we're going to be seeing shortly. A is a quantity that is proportional to the mean wind speed at a location. So if you had like a little pilot study and you at least know, hey, the mean wind speed is somewhere around, let's say, 4.5 meters per second, okay, there's a way to compute A from that information, and now you're fitting your Weibull distribution, so now you have a sense of how often the wind speeds will be occurring with speeds greater than 15 meters per second, or greater than 20 meters per second, or whatever. And so given a value of K, the shape parameter, and a value of A, the scale parameter or the location parameter, there's this Weibull distribution is actually a graph of a curve with this horrible looking equation. It is a graph of this F, which is a function of U, the wind speed, and you could do this equation, and it's awful. I mean, nobody's going to like that equation. Oh, there's some math major who's going to think that's a beautiful equation. But by and large, this is a horrible looking equation. But something is making me uncomfortable about what we're seeing here. I'm still not loving the fact that we don't know what that y-axis is. I mean, I have some intuition that it's somehow about how frequently or how frequently that observation happens, or what the probability of that observation happened, but I don't know yet what I feel like that is. I mean, what is that y-axis supposed to be? Okay, a good guess might be probability. Like it's a number between 0 and 1 that tells you how likely it is to get that observation. Let's try that. Oh, this is such a good teaching technique. I'm going to show you something that's not going to work. Okay, I'm going to tell you in advance that the y-axis here is not probability, but let's find out why. All right. If that were true, if that y-axis there was something like probability, what I would do is I'd say, well, what's the probability that I have a wind speed of 5 meters per second? Then I could go over there on the x-axis to 5 meters per second, read up and across, and I'd get something like 0.075. In other words, like a 7.5% chance that my observation is going to be, my wind speed is going to be 5 meters per second, based on the location's values of K and A. Okay, maybe. And let me just try a second one here. What would be the probability of the winds being 7 meters per second? I could go over on the x-axis to 7 meters per second, follow that dashed line up and read across, and I'd see that that has a probability, if that's what this really was, of 0.7 or 7% based on this location's value of K and A. And at first that might not sound horrible. But something very bad has just happened. See, if that's what the Weibull distribution is telling us, we have a very serious problem. But to see the problem, I need to point you to the fact that when we were figuring out problems about probability, the word OR means to add probabilities. The probability that I will have a Big Mac for lunch or a Whopper for lunch is the probability that I'll have a Big Mac for lunch plus the probability I'll have a Whopper for lunch. Okay? Or, when we're talking about probability, means to add the chances. So if my probability, notice my notation here though, if the probability that the U wind speed is 5 was this 0.075, and the probability that my wind speed was 7 was this 0.07, which I'm not yet confident is a bad idea, then the probability that the wind speed is 5 or 7 is the probability that it was 5 plus the probability that it is 7, which is 0.145, which again doesn't sound horrible, but it's illuminating the fact that something has gone horribly wrong. See, I could just keep adding more chances, like the probability that the wind speed is 1, or the probability that the wind speed is 2 meters per second, or the probability that the wind speed is 3. And I could keep adding and just keep adding more probabilities here, and sooner or later we're going to get better than 1. We're going to have a probability greater than 1. And while it's true we have hit a lot of wind speeds here, like the wind speed is equal to 1, or the wind speed is equal to 2, or the wind speed is equal to 3, what about 1.5? Or 1.4, or 1.45, or 1.457. We haven't hit any of those probabilities yet, those possible wind speeds, and we're already breaking the laws of probability by having a probability greater than 1. There's no such thing as a probability of greater than 1. We have, by some kind of reductio ad absurdum, or however that expression goes, we have proven, I don't know what that y-axis is, but it is not probability. Because by doing something perfectly reasonable, like what is the probability of this wind speed or this wind speed, I broke this. I made it so the probability was greater than 1. So is that probability, is that y-axis actually probability of these wind speeds? No, that does not work. And there's another way you could prove this to yourself. Thinking back to the first part of this lecture. What really is, I was saying that did that mean that the probability that the wind speed was 5 worked out to like 7.5%? What is the actual probability that the wind speed is 5 meters per second? The answer is, shockingly, is 0. Remember, the actual wind speed is an irrational number. It doesn't have anything to do with rational numbers or integers or anything like that. The wind speed is never, ever, ever exactly 5 meters per second. It might be really close to 5 meters per second, but it's an irrational number. It's going to be something like 5.00001234731 or 4.999385. It could be really, really close to 5, but it's not ever going to be 5. The truth is, the probability that the wind speed is 5 is exactly 0. So clearly what this diagram is showing here is not probability. Not a graph of probability. What is it? You're going to hate that. It's a graph of what's called the probability density function. Probability density function, or PDF. It is not the same thing as probability, because what we can get a sense of the relative likelihood of outcomes. I can look at this graph and say 5 meters per second, that is more likely, wind speeds around 5 meters per second are more likely than wind speeds around, let's say, 25 meters per second, because it is taller. But the probability density function itself, which is what's plotted here, is not a probability itself. Instead, if the probability the wind speed is 5 is actually 0, it'll never happen, or if the probability of the wind speed is actually 10 is 0 because it'll never happen. But the reality is there are real numbers that are the wind speeds. And there's a real probability that the wind speed will be between 5 and 10 meters per second. That's what, like on that bottom line there. The probability that 5 is less than a wind speed, which is less than 10. There's a real finite probability that we are in that range, which is what I've highlighted in red. That area that is in there in red is a probability. On this diagram, area is probability, not the height, the area. And the probability that their wind will be between 5 and 10 meters per second is a real number. It is a number that we get from computing an area, and And you probably have survived enough math classes to know where that's going. Integrals. The probability that the wind is between, in this case, 5 meters per second and 10 meters per second, is the integral of the probability density function, the PDF. We need to take the integral of the probability density function from 5 to 10 to get that area. And that area will be the probability. It will actually be the probability the wind speed is somewhere between 5 and 10. And so we have to literally compute that probability, like I have up there in the top left corner. The probability that the wind speed is between 5 and 10 is the integral from 5 to 10 of that horrible expression that is our probability density function. And that does not look like much fun. And unless you really feel like digging around in the back of calculus books or have a really good, powerful sense of how to use tools like Wolfram Alpha online to help you compute difficult integrals, odds are you do not like that expression. It actually isn't the end of the world. You can dig around in the back of your calc book and figure out this one. But trust me, it will work. You're not going to do the integral because that's not where we're going with this class, but it would work. It would give you a finite, real probability that is the chance that the wind speed is between 5 and 10 meters per second. It's not the height of the curve, although the height of the curve is part of the story. It's the area under the curve. Similarly, we could do the same sort of thing and find the probability that the wind speed in any given observation will be between 20 and 25 meters per second. And we could take the integral of our probability density function, but integrate it not from 5 to 10, but from 20 to 25, and we would get the probability that the wind speed is between 20 and 25, and it will be a probability. It'll be a number between 0 and 1. It will be a smaller number than it was for between 5 and 10, because we are now talking about something that's less likely to happen. But this would work. Again, it would be awful. It's going to have all kinds of probabilities that it's going to have all kinds of properties that we like. For example, the area under the whole curve is going to work out to 1.0, because 1.0 is 100% chance. You're basically saying that the probability the wind speed is between 0 and infinity is 1, right? You're absolutely 100% certain your wind speed is somewhere between 0 and infinity. It can't be anything else. And you could in fact show that if you integrate that probability density function from 0 to infinity, it works out to 1, which is pretty slick. There's a lot of these kind of properties that make a stats major very happy, okay? That's part of what makes it a probability density function. And just to give that vocabulary word here, again, if you just ask Google to find probability density function, you get a card that reads that it's a function of a continuous random variable. In other words, a variable something that you observe and can have any value, whose integral across an interval gives the probability that the value of the variable lies in that variable, lies in that interval. So like if you want to know what's the probability that the wind speed is greater than 20 meters per second, you will integrate that probability density function from 20 to infinity. Because you're saying any place between 20 and infinity, what are the probabilities that will happen? Or what is the probability that the wind speed is less than 20? You would integrate from 0 to 20. I will leave it to you to solve that. Now, you're not going to do these integrals. They're horrible. But this is how these probability density functions work. Is they kind of, in an intuitive way, that y-axis kind of helps you see, oh, I see. It's more like these observations are more likely at values on the x-axis where the curve is high. They are less likely where they are low. But that's not, it isn't a probability, it isn't a frequency. There's no good label for what's going on the y-axis. It's unitless. We are instead going to be integrating over this to then figure out what the probability is. The probability would be proportional to the area under the curve between the limits of the range that you're trying to find. Now that's what the probability density function, or PDF, of the Weibull distribution tells us. It gives us it explains the distribution of wind speeds over a long period of time. You'll have this much of the time, you'll have winds in this speed range, this much of the time you'll have wind speeds at this range, and so on. But it's always the case that actually doing these integrals is no fun. In general, that's not what you're going to want to do, and in the case of the Weibull distribution, you don't have to. Instead, as long as we set the problem up right, we can work with a standard solution to that integral that will solve things for us. For example, let's say I wanted to evaluate this one again, where I wanted to know the probability that the wind speed would be between 5 and 10 meters per second. Okay? Now, in order to do that, pick the middle number between, the average or whatever, between 5 and 10, so like 7.5. That'll be our value of u. And then define delta u to be a number that is like how far it is, so that your range is u plus or minus delta u. So now we want to find, so in this case it'd be 2.5, so that our range goes from 5 to 10. It's 7.5 plus or minus 2.5. So what we want is an equation that gives us the probability that the winds, according to our Weibull distribution, will be between u and delta u. Well, it turns out clever math sorts have done that. And the equation is as follows, where your probability, the chance that the winds are in that range, is, and then it's this equation that's got k, your shape parameter, and a, your scale parameter or your location parameter, and it's got a delta u and a u in it, and it doesn't look any fun, but this is what calculators and spreadsheets are for, and so on. And you can compute this value to find out what the probability the winds will be in some range. Neat! Often what we'll do is repeat this calculation over and over again. So like you'll first do, let's just say u is equal to 1, and 0.5 is equal to, and delta u is equal to 0.5. So you're figuring out the probability the wind speed is in the range 1 plus or minus 0.5. So it's from 0.5 to 1.5. And then you'll find the probability that you do the same calculation again, this time with u equal to 2 and delta u still equal to 0.5. So now you're figuring out the probability that the wind speed is between 1.5 and 2.5. And then you'll do the same thing again for 2.5 to 3.5 and 3.5. And you can make yourself like a little bar graph then that shows the probability the wind is in each of these little ranges and so on. This is a very powerful tool. But it is a tricky tool to use until you've had more experience with these things and so on, which is why in your homework set you will actually be cranking some numbers. You won't actually be doing any integrals. You'll be using that equation that you have there. That is the form that will work best, where you have that p on the left-hand side, and then this, on the right-hand side, this form with u and delta u in it. That will be a very handy form where the integral has already been solved for you. Okay. This Weibull distribution is a powerful tool. It tells us a lot about the characteristics of winds that our wind turbine is going to be encountering over its lifetime. We will know, well, what is the probability of winds greater than, let's just say, 25 meters per second. If your turbine has to go through some expensive shutdown procedure when the wind exceeds some limit, how often is that going to happen? The Weibull distribution can tell you. Once you know something about K and A, the shape and location parameters, based on like a pilot study or something like that, you can determine the probability that the winds will be greater than 25 meters per second, even if during your pilot study the winds were never more than 25 meters per second. Maybe your pilot study wasn't long enough to ever have encountered those strong winds. But now you can tell us something important about how often that's going to happen. Or like maybe your turbine doesn't generate any power at all if the wind speed is less than 2 meters per second. Again, what fraction of the time will that be? Oh, well now we can start sorting that stuff out. Ooh, these are powerful ideas, and they're really going to help us when we start trying to figure out things about the distribution of the winds and the frequency at which we can observe certain winds and so on. That wraps up lecture part 2 of this lecture, in fact the entirety of this lecture. Before we go on though, I do want to ask you a couple quick questions. Question 6. The Weibull distribution models the distribution of wind speeds, telling us that weak wind speeds are blank than very strong wind speeds. Much less common or much more common? How are weak winds related to, the frequency of weak winds related to the frequency of very strong winds according to the Weibull distribution? Make a choice from your 2 options and get a little feedback before you move on to question 7.